Hello and welcome to the 73rd Porous Media Tea Time Talk. We are part of the InterPore Young Academy, where we are giving the chance and the opportunity to the early career and young researchers around the world to present their research on the various aspects of porous media sciences as part of the InterPore Academy. Today, we have the pleasure to host two excellent young researchers from the InterPore Spain, who won the InterPore National Chapter Award last year, and today we are honoring their young researchers. And as the first speaker, I'm happy to introduce Caterina Landi. She's a third-year PhD student at the Complutense University of Madrid, where she's currently working on simulating and modeling active systems. Caterina holds a bachelor degree in physics and a master's in biophysics, during which she developed a strong interest in modeling of biological systems through numerical simulations. During her master thesis, she became passionate about active matters, a branch of soft matter which is focused on systems composed of self-driven units, leading her to explore the fascinating world of active polymers and gel-like structures. We are really happy to have Caterina with us today. Welcome, Caterina, and the floor is yours.
Thank you. So good morning, good afternoon, everyone. And I'm going to, here to present my work. So this is briefly a description of what I'm going to talk about in this talk. So an introduction to active matter for those who don't really know the field. Active filament, moving to a specific active filamentous matter. Then asking ourselves the question, how can we simulate active filaments? And then working a bit on, trying to reply to this answer. We're explaining why it is convenient in our case to move from temporary bonds to fixed bonds in our simulations, and then ask the final questions when active filaments are able to form gel-like structures. So active matter includes all those systems that are whose elements are able to self-propel, so to get the energy from the environment and to transform it into directed motions, persistent directed motions. Since energy is, these systems can be considered intrinsically out of equilibrium, since energy is dissipated continuously, and they span different scales in nature, from the nanoscales with biomolecules to the microscales with bacteria or sperm cells, but also with synthetic particles as the Janus particles. And then we can also move on the macroscales with animals. And so, as we said, these are physics that is at non-equilibrium, so can only be understood in the framework of this concept. Why these systems are particularly interesting? They are interesting because they show collective behaviors that are not observed in the corresponding passive systems, as for example the motility-induced phase separation. So if we take a system of colloids that are purely repulsive, they are able to aggregate to form clusters even in the absence of in the absence of attractive forces, and this is due only because of activity. So basically, because two particles they can meet each other, and then to do their persistent motion just get stuck, and then if they don't reorient in time, other particles can come and then they can form clusters, and the clusters can grow and then can change size and shape. And another interesting example that I like to show is the flocking of birds. And I'm not going to get into the detail of this model to describe these interesting collective behaviors, since it's not exactly what the presentation is about, but just out of curiosity, I wanted to show it to you. And basically, the way the birds can can form this beautiful shape while flying is due to alignment. So they align with the neighbors, force, and in doing so, they follow each other and they form this special force. And with active matters, active models, we're able to model these behaviors. But in particular here, I want to focus on active Brownian particle model. There is an active model to describe Brownian particles that are active, so other than they follow the Brownian dynamics with a propulsion term that is due to the fact that they are self-propelling, that are active. They have a fixed self-propulsion. In particular, very interesting, very rich is the dynamic of active filamentous matter, because of their elongated shape, their anisotropic shape, So here I'm just showing some examples. So as, for example, active filaments that are structures present in the cytoskeleton of the cells, or as, for example, bacteria and worms that have elongated shapes, or also as, for example, colloids that can form, here I'm showing a video, colloids, and we can self-assemble Janus colloids. There are colloids they have two different materials on one side and on the others, and due to the attractions forces that are established between two colloids, we can form this chain. So there are a lot of examples in nature of active filamentous matter, but also synthetic one. And I wanted to show here just a few. To understand, to give you a bit of the context why we are interested into modeling these systems. And so how can we simulate active filaments? We worked with Professor John Russo and Francesco Sciortino from La Sapienza Università di Roma, trying to simulate active filaments. So how we simulated a two-dimensional suspension of active bifunctional Brownian particles. They are bifunctional because they are basically hard particles with two attractive sides. So that's why they are bifunctional. And these two attractive sides are at the opposite ends of a diameter, such a way that when they self-assemble in a chain. And on top of that, we added activity along the diameter connecting the two sides, the two attractive sides. Here I'm citing the work of Sciortino, that is basically the theoretical study of this model when activity is not present. And we use this work as reference for all our analysis for this for a comparison of our results with their results, to see what's the effect of activity in the case we have this suspension of filaments. And so these particles are active, bifunctional, but they're also Brownian, so they follow Brownian dynamics. So we have the noise in rotation and in rotation and in translation. Then we have the self-propelling term. And then we have the external torque and external force and external torque that are, of course, connected to the interaction potential. There is a pair potential between two particles, and that here I'm just showing into the slide. And that is made of two terms. There is a term that represents the interaction between the center of mass, and a term that represents the interaction between the sides. So one that represents basically the repulsion between the hard cores. The particle cannot penetrate into each other. And the other one is the attractive of the sides. So we have repulsion and then attractive depending on the distance between the two particles. Just a description of the model. Then we simulate our system for different temperature, density, and Peclet number. For those are not into the field of active matter, the Peclet number is an a-dimensional number that evaluates, compares the activity, the level of activity compared with the level of thermal fluctuations. So the noise that we have. So here I present a phase diagram of our simulations at a fixed temperature and as function of the Peclet number and of the density. The Peclet number is increasing from left to right and the density from bottom to top. And in the case of we have no activity, that's the one I'm showing, the left column, particles self-assemble in linear chains that are uniformly space distributed. And in the case, whenever we introduce activity, these particles starts to form, to self-assemble in linear chains that are aggregated between each other on a different level, depending on the density and activity. We first characterize, of course, the system. So we evaluated, here I'm plotting two the chain length distribution and the structure factor, so two characteristics of the systems. The chain length distribution is measuring basically how the distribution of all the lengths, and they are following an exponential distributions, we can see, and increasing the activity, the slope of this exponential is decreasing, indicating that the activity is basically breaking the chains. So more activity, the chains are smaller, shorter. And also the structure factor is also giving us another information, the fact that these chains, these filaments are aggregating, and we can observe this because we observe a peak in the case we have no activity that is due to alignment, because when chains are aligned, they have a characteristic distance, and we can see this characteristic distance in the rise of this peak. When these chains are aggregating, so we have no characteristic distance between chains, this peak disappear, and this peak disappear with increasing activity. So we can say that activity is breaking the chains and is inducing aggregation among the chains. Also here, I'm not going to get into detail on how we evaluated this quantity, but the importance of what the message that I wanted to convey is that the self-assembling is occurring randomly at low activity, but is favoring alignment of the activity, favoring an alignment of the self-propulsion vectors when activity is high. So in this case, in this system, we have a distribution of velocity in the filament lengths. Here some particular phases. When we were playing with the system, we at different temperature, different density, different level of activity, we noticed the formation of a hexagonally ordered structure at quite high activity and quite high density. And this is probably due because chains in a range where chains are small enough, so we need to shift in the phase diagram where activity is high enough, and these structures that is quite compact can be observed. On the right, I'm showing the formation of the crystal. For reasons of time, I'm not going to get into detail of this, but you can see quite clearly what's happening, how it's forming. This is explaining, this crystal is also rotating and is showing why. And also another interesting phase was the motility-induced spiral phase. So this, they at intermediate activity, so when chains were long enough and not too dense or not too low to dilute the system, they were forming these spiraling structures. They were quite interesting. But in order to better study this, what we decided to do, since it was kind of hard to study the system where the bonds were not fixed, but the bonds were breakable, so we're able to form and to disassemble and form again, we decided to fix these bonds. So to study a new system where we have chains of different lengths, but these chains cannot break. So they are given at the beginning of the simulations and they are fixed, of a fixed length. And this is in particular the equations that we're going to integrate. Also we don't really need to get into the details of this. If the message, the important things, the difference between the previous simulations that we fix the bonds. So this is the message. And we tried to study a bit of the system in this case to understand more a bit the spiraling structures that we were observing into the system. And we decided to evaluate this quantity, that is the turning number. So the number of turns that a filament make between its own ends. I'm plotting here the turning number as a function of activity of the Peclet number, and with different color are the filaments of different lengths. So 71 beats or 11 beats, different beats, Short filaments, of course, they have the turning number close to 0, as they are too short to form proper spiral filaments. And as we increase the length of these filaments, or medium-long filaments, they're able to wind into spiral structures and progressively also unwind. So there is a reentrant phase behavior. So they form spirals, but then increasing too much the spiral, they open up eventually. And also, if we play with a system where this is on the left, I'm showing the mechanism of formation. So basically, the longer filaments they tend to wind, to coil around the smaller filaments to include them, and then just form these kind of like nested spirals. Here I'm showing the number of filaments in a typical of what we call nested spirals, and is going towards 2. So basically, we start low activity. We have usually nested spiral formed by many filaments, and then at the end, only 2 filaments. Another quantity that here I'm just briefly showing, I think is interesting and relevant to the description of the nested spirals, is we take a nested spiral, we evaluate the length of the minimum and the length of the maximum filament into the nested spiral. And of course, we observe this quantity going with increasing activity towards the minimum possible value, meaning that in the case of a high activity, we have usually nested spirals that are made of only 2 filaments, one that is very big and one that is very small. So basically, one big filament englobing a small one. So we have kind of like a capturing mechanism, something where we can trap smaller filaments, or maybe even like just small particles. And here I'm just showing the dynamics of these filaments, and is proving what I've just said. So basically that longer filaments are englobing them, and the dynamic is influenced by that, of course. So then towards the last questions, the question that we made was when active filaments form gel-like structures. So in order to obtain gel-like structures, we need to introduce activity between the filaments, attraction between the filaments. That's the way we can do it if we have filaments. So we studied filaments where we have an alternative red and blue, red and blue, red and blue along the whole chain, along the whole filaments, and alternating different type of monomer of beads. The blue one are attractive. The red one are simply repulsive. Okay, so the attractive one, they are the one that offer the branching points and the possibility to form gel-like structures. Here I'm plotting here a phase diagram as function of activity. Activity is still tangential to the polymer backbone, so is as in the previous model. And here I'm just showing a phase diagram. In order to obtain gel-like structures, we need to be at higher density than the one we were performing before, because not too diluted, otherwise we see the spiral structures that we were observing, and not too dense, otherwise we just see something that is kind of like more glassy, or more that is not fluid, that is just solid. So intermediate density, and at the moment we are just trying to characterize a bit the structures, and for example studying the radial distribution function, but also the percolation probability, because that's what will help us to define when we are working into a gel-like structures. But still, this is a work in progress. We are just started to work on this. So I will just thank you, and giving you the possibility to read a bit of what I've worked on, and if you have any questions, you can also find it there. So thank you very much.
Yeah, thank you very much, Caterina. It was extremely interesting presentation. Thank you for sharing your results with us. Before I read any question from the audience, I will start with a question from my own. It's my own curiosity. If I am correct, you found that this neat behavior, that active particles, they make shorter clump chains compared to the longer and spread out connections in the passive systems. Can you tell us a bit more about how did you found them, and what's interesting about them, and what would be the difference between these two behavior between the active and passive systems in terms of the length and behavior.
Sorry, I don't know if I understood correctly, but you're talking about the difference, because I missed the first part of
in your active particles, you are showing a shorter clumped version of the chains compared to usually longer and spread out chains that we see in the passive systems. Can you tell us more about these, your observations?
Okay, so you mean about the angular, you mean?
Yes.
Or
and also their lengths, the behavior of the chains.
Okay, so about more or less like this, that's what you meant?
Yes,
yeah, because I'm missing some words, so I don't know if I understood correctly, but I mean, I hope that I got the message. So some information about what's the concept, I mean, the description of what we see and the relevance maybe of this, right? Of the difference that we observe with the passive system. Yeah, I would say that, I mean, the reason why we're doing this is trying to model maybe real systems, so biological systems, and we're in this case, I mean, we observe that in the case we have sometimes whenever in the case we have active filaments, we have some aggregation of these filaments, right? And even here, maybe I think I can show more. Or even here, they show particularly interesting collective behaviors, right? And so there is what we wanted to understand is why they behave so different from the passive case, and to model and to understand how different they are. And I mean, whenever we model with this method, we observe that whenever they are passive, they are homogeneously distributed. Whenever they are active, they tend to aggregate, and this could mean, for example, that we have a separation of phases. So, I mean, the potential of this could be to understand how we can use active filaments to, I don't know, maybe drug delivery, kind of like, because we can, for example, active filaments, right? They are structures that are inside of our cells and that are active, right? So if we are able to, by introducing active, activity inside of these structures, so filaments and so on, we can use a phase separation. So the rise of new phases that were not observed in the case these filaments are just passive. So for example, I mean, there could be some application to induce a phase separation, or as we were saying before, like englobing mechanisms, so trapping mechanisms, and then cargo delivery maybe of the structures that we were able to wrap around, or also maybe separate, maybe if we want, I don't know, some type of filaments from other, because at the end filaments are also proteins, can be, so like every type of filaments that we have in our body. So yes, I think they will be the interesting part of this, will probably some application into the medical field, and they rise from simple models. So the simple Brownian motion, where we introduce some activity along the polymer backbone, for example. So yeah, I don't know if this,
Yeah, you covered it very nicely. Thank you very much. Now let's move on to our second speaker of today. Our second speaker is Animesh Nepal. He is a PhD student at the Spanish National Research Council in Barcelona, Spain. His research focuses on cyclic two-phase flow in porous media, in particular on pore-scale processes that results in pressure saturation hysteresis. Nepal combines numerical simulation with microfluidic experiments in his research. Thank you, Animesh, for joining us today, and the floor is yours.
Thank you. Today my talk is about interface jumps, spinning, and hysteresis during cyclic fluid displacement in a singular pore using three different approaches: numerical, experimental, and analytical. Okay, how can I? Okay, I cannot change my slide. Sorry. Oh. I'm sorry, my slides is not changing.
Maybe if you use Alt and Tab. if you are using a Windows machine, then you go to your slide and then you would be able to change your slides.
Now can you see?
Yes, now we can see.
Okay, perfect. Sorry. So cyclic fluid displacement is prevalent in many processes such as hydrogen storage, CO2 sequestration, oil recovery, and so on. In cyclic fluid, displacement in porous media is characterized by pressure saturation and hysteresis. On this figure to the left, you see on x-axis is saturation, on y-axis is pressure, and during imbibition and during drainage, this pressure saturation curve follow two distinct paths, thereby creating this hysteresis loop. So what's happening here is during two-phase flow, this pore scale variability in porous media leads to variability in interface curvature as this two-phase flow moves inside the medium. And this variability induces local instabilities. And these local instabilities especially can especially align and drives and driving coordinated front movement, also known as hinge jump. So in order to study this, we chose this ink bottle setup. Ink bottle is basically a cylindrical tube with two different radius R1 and radius R2 in this slide, and it's connected by a cone, which has this cone angle of alpha. And the reason we chose this is because this ink bottle shows a saline feature of capillary action in a pore, and it also enables us to understand the detailed mechanism and controls of the capillary hysteresis. The objective of this work is to investigate the influence of pore geometry in capillary hysteresis. For this, we chose two different approaches. One is quasi-static pressure-driven, which is also known as P-driven, and quasi-static volume-driven, which is also known as Q-driven. And in quasi-static P-driven, what we do is we change pressure at the inlet in very tiny amount. We wait for the system to equilibrate, and we change the pressure again. And in volume-driven, instead of pressure, we inject volume. So we do this, we wait for the system to equilibrate, and we change the volume at the inlet. So the experimental setup for P-driven, as we see in the center of the figure, is ink bottle, whose inlet is connected to a reservoir which supplies the fluid. This reservoir is fixed to a platform which can be raised, thereby increasing the pressure at the inlet, and lowered, thereby decreasing the pressure at the inlet. On this figure, on the left-hand side, we see experimental results for P-driven, pressure-driven. On the top is imbibition images, captured images, and on the bottom is drainage captured images. On the bottom of the figure, we see a number which corresponds to the inlet pressure, and the numbered and the number are just the number going from 1 to 7 during imbibition and from 8 to 14 during drainage. On the left-hand side, we have pressure height curve. Pressure is on the x-axis and height is on the y-axis. The markers corresponds to the jury inside during experiment, and blue color corresponds to drainage, and red color corresponds to imbibition. And the vertical line joining this green markers corresponds to hinge jump. And as we can see in this figure, this jump occurred at different pressure during imbibition and drainage, thereby creating this hysteresis loop. We ran the numerical simulation in OpenFOAM. The simulation was 2D. We solved Navier-Stokes equation. We employ volume of fluid method to differentiate two different phases. We ran three different numerical simulation with varying conical angle. So the only thing that is changing between these three simulations is the conical angle. So the first is 10 degrees, 6 degrees, and third is 2 degrees. The contact angle in all of these simulation was 45 degrees. And as we can see, for alpha equals to 10 degrees and alpha equals to 6 degrees, there is a formation of hysteresis loop, whereas we do not see any hysteresis for alpha equals to 2 degrees. So basically, in conclusion to this slide, is that the magnitude of jump and the size of hysteresis decrease as with decreasing alpha. Then we derive the analytical model for the interface height during pressure-driven quasi-static imbibition and drainage in an ink bottle. The ink bottle is divided into 3 different cross sections. So cross section 1 and section 1 and section 2 is the upper and lower cylindrical tube, whereas section 2 is the conical part that connects section 1 and section 2. We derived this analytical equation for the urine side by pressure balance across the interface, which is capillary force with hydrostatic pressure, capillary pressure, hydrostatic pressure, and the pressure at the inlet. And what we observe is, for section 1 and section 3, the dependency between urine site and external pressure was linear, whereas the equation was quadratic with respect to H for the conical section. As we can see, H is on the left-hand side and also on the right-hand side. In the next few slides, I will talk a bit about the causes of interface jump, pinning during imbibition and drainage. So during imbibition, the interface height rises as the external pressure rises at the inlet. The interface height in the conical section can be calculated using this formula. This formula, as in this formula, we see this delta, which is discriminant, and if this delta is negative, the interface jumps. If delta is positive, the interface moves into the conical section. And for this experimental image that we saw before, we see that the interface moves inside the conical section because delta was positive, and as it reaches somewhere in between H1 and height H2, the delta becomes negative and it jumps beyond height H2. We can calculate the critical cross-section gradient by solving this discriminant equation for alpha. If the angle of the conical section is greater than the critical cross-section gradient, this calculated critical cross-section gradient, interface jumps at height H1, and we see during numerical simulation, the interface jumped at height H1 for both alpha equals to 10 degrees and alpha equals to 6 degrees. For alpha equals to 2 degrees, there was no jump at all because, as we saw before, there was no the pressure saturation trajectory was fully reversible. And that's because in both this alpha equals to 10 degrees and 6 degrees, this alpha was greater than the critical alpha that was calculated. During drainage, the interface height decreases linearly with external pressure, and upon interface arrival at height H2, it experiences change in curvature of the interface. So if the contact angle is greater than the half of the conical section, or half of the angle of the conical section, interface gets pinned at height H2. But in experiment, it was less than half of the angle of the conical section. Interfaces dropped upon arriving at height H2. But in numerical simulation, because contact angle was greater than the half of the conical angle of the conical section, we see pinning of the interface. Pinning is characterized here by the straight line, as we see in alpha equals to 10 degrees and alpha equals to 6 degrees. To further illustrate how meta-stability of the interface in the conical section affects imbibition and drainage, we derive the energy function, or also Hamiltonian. In this figure, the energy function corresponding to the numerical simulation, alpha equals to 10 degrees and alpha equals to 15 degrees. All these curves are for different driving external pressure at the inlet. And this marker corresponds to the interface position or zero inside, red for imbibition and blue for drainage. There is a single energy minima when the interface is in the lower or upper tube. But as we get close to this conical section, or the vicinity of the beginning and end of the conical section, the energy density can become metastable depending on the external pressure. For the numerical simulation, which is alpha equals to 10 degrees, we see upon interface arrival at height h1, the minima of the energy quickly shifts from height h1 beyond height h2, so we see there's a jump. But during drainage, the interface is pinned at height z equals to h2. Because the local energy minima at height h2 is not unstable, and interface become unstable only when the external pressure is lowered further. So as we see in this part, we see interface spinning. The interface drops when the external pressure is reduced substantially, and then the interface moves lower than the height h2. But in experiment, the interface at height alpha equals to 15 degrees, the energy has single minimum when interface reaches height z equals to h1. Only when external pressure is further increased and goes beyond the critical external pressure, jump occurs. During drainage, the interface is not pinned at height h2, and it becomes unstable and jumps at height z equals to h1 during drainage. So this was all about pressure-driven quasi-static imbibition and drainage. So what I will talk next is volume-driven quasi-static imbibition and drainage. So for this, we also derive analytical model for the interface side. The parameter that the control parameter now is VT, which is volume that we inject into this conical into this ink bottle, and because we know the height, because we know the volume of the cone analytically, we can calculate the attained height, the height that liquid will attain given the injected volume VT, which is height HE in this thing here. So lambda is Lagrange multiplier, which is also the pressure that we measure at the inlet as we start to inject. So this is the analytical model. We then ran numerical simulation in two different setup, which is alpha equals to 10 degrees and alpha equals to 20 degrees. The contact angle is constant for both of the simulation run, which is at 45 degrees. What we observe is the pressure saturation or pressure height curve was fully retraceable, both during imbibition and drainage for both these curves. And this analytical model that we derived was also closely fitting with the numerical simulation data points. So in conclusion to this slide, the pressure saturation trajectory does not show hysteresis during Q-driven displacement, unlike P-driven, where we saw pressure saturation hysteresis. So we further derived this Hamiltonian for volume-driven quasi-static imbibition and drainage in an ink bottle. These lines are for different control parameter. So as we go up, this external volume that we inject increases. So as we increase this zero inside, which is marked by this marker, goes to the right. And this here, we also see that there is only one possible solution, a possible position for the interface to attain. So there is no metastability, there is no hysteresis. This is what we also observed in the previous slides for Q-driven. So in order to conclude, For the angle of the conical section greater than the critical angle, the interface shows metastability that leads to interface jumps and hysteresis. The magnitude of the jump and the size of the hysteresis cycle increase with increasing alpha. The interface is pinned at the end of the conical section if this contact angle is less than the angle of the conical section, less than the half of the angle of the conical section. And unlike P-driven, unlike pressure-driven, in volume-driven, the pressure saturation pressure height path does not show any hysteresis. So you can also find this work in this published article. And I would like to thank my sponsor and thank you for your attention. Thank you very much.
Excellent. Very interesting talk, Animesh. You certainly did a lot. And the fact that you try to combine analytical, experimental, and numerical simulation was really fascinating. If you want to summarize the similarities and differences of pressure and volumetric-driven hysteresis, what would you say? What are the main influencing factors, and what is the consequences for two-phase or multi-phase flowing force media?
Yeah, I think the main difference between these two things is, so in one, so in pressure driven we see this hysteresis, like jumps, and although we also saw pinning of interface during volume driven, we did not see any hysteresis during volume driven. So the common thing I would say is the interface pinning, which we also saw in volume driven, but pinning did not necessarily lead us into hysteresis, which we saw in pressure driven. Yeah.
And
so I mean the application would, I mean, I could think is like you could make a porous medium in such a way that you want to have less energy dissipation. If you want to design a porous medium, then you can use this this approach that we derived in order to like calculate the angle, like which angle would you then have to make less, less jump and less energy dissipation. So you can use this to design a porous medium, but you can also use this to sort of calculate how much you dissipate energy in a real porous medium, where you cannot manipulate these pore spaces and angles and stuff like that. So yeah, I guess that would be the sort of application.
Yeah. And I would assume that you would consider a critical pore diameter to see these differences. Would you see the same effects on the usual reservoir rocks, for example, the sandstone reservoirs that you see for petroleum resources, CO2 resources, or hydrogen storage resources? Would you see the same range of critical pore diameter there?
Yeah, that's very interesting, because we only look at sort of one pore, right? So in reality, there are always sort of interacting pores, which is affecting. Yeah, one pore will affect the other pores. So it's hard to tell. Like we could really sort of make a corollary argument with porous medium, but yeah, sounds interesting, and that's what I'm looking at the moment in my next work. Yeah, I'm looking at this mechanism in porous media.
Excellent. Okay, thank you very much. I guess we have a question that comes from Dario Sinandra. Hi, Animesh. Thanks for the talk. My question is about upscaling of the model. How can you upscale this alpha angle to complex porous media? That's extremely tough question.
Yeah, I know Dario. Yeah, that's a good question. I don't know how to do this at the moment. I mean, that is our original. That was our original idea at the beginning of my PhD, to upscale these processes into larger scales. Yeah, I'm gonna have to talk with Dario a bit later. I don't know the answer at the moment.
Okay. Yeah, thank you to you both, to Animesh and Caterina, for joining us today. I personally enjoyed and learned a lot, and I hope our viewers that are online and those who will follow up usually after the session will appreciate this very interesting research that is being presented today. With that, I would like to close the session and thank you all, and also invite you to next cross media tea time talks that would be in the middle of the November. With that, I thank you and say goodbye. Bye bye.
Thank you.
Thank you very much. Thank you for having us.